So let me solve the second question, which is a design question. I'll share my screen. So the second question says a straight trapezoidal channel will be excavated into clay having a void ratio of 0.3. The channel will have a bottom slope of 0.0016 and it will convey a discharge of 18 meter cube per second. Proportion the channel section, and it says take n Manning roughness coefficient is 0.02 and our small z is 1.5. So basically it's a trapezoidal channel, so we need to design a channel something like this. So this b is bottom width, this y is the flow depth, and this t is the width of top portion of the flow, and this small height difference, this small depth difference between the top portion of this water flow and this channel is called a freeboard. We need to decide these dimensions basically. How can we start? We can start by deciding what is our permissible unit tractive force. So how can we do it? If you go to the open channel 2 lecture notes, in page 58, let me show you, you'll see a graph, something like, you'll see a graph like this. In the x-axis, the void ratio is given and the curves are defined for different types of soils. We have, in our question, we are using clay and our void ratio was 0.3. Therefore, from 0.3, we will go to the clay curve, which is this one. We will read our permissible unit tractive force from the y-axis. So here you can see it is 2, but be careful about the unit. Unit is kilogram force per meter square. So I just wrote it here, 2 kilogram force per meter square, but I want to convert it into newtons. So 1 kilogram force is 9.81 newtons. Therefore, if I multiply this 2 with 9.81, I will get 19.62 newton per meter square. After that, we need to assume a B-Y ratio. I assume there's 4. We assume this ratio, then we will calculate our dimensions for this ratio. At the end, we will calculate the design discharge. If this design discharge matches with this demand discharge, we'll say, okay, this is a acceptable design. If it doesn't match, we will say we need to design one more time. We need to make another assumption, and we need to repeat our calculations. So I assumed as 4. So by using this B over Y ratio from figure 1, we need to decide our maximum tractive force. It is in page 55. So let's go to the page 55. You can see here there are 2 graphs. We want our maximum tractive force on not on the sides but on the bottom of the channel. Therefore, we are going to use this second graph. So we have trapezoidal channel. So we are going to be looking at this the curve on the top, and our BY ratio was 4. I'm going to the trapezoidal channel curve, and again I'm reading my C1 value from the y-axis. You're reading by your eyes, so in my opinion it's like 0.96 or something like that. And after find C1, by using this equation, we will calculate our maximum unit tractive force. So C1 is 0.96, and by using that ratio, that equation, what is the equation? C1 times gamma times y times S0. So C1 is 0.96, gamma water is 9,810. We don't know why. We know what is the slope. It was 0.0016. This is the maximum tractive force. Here, what we need to do is we will equate this maximum tractive force to our permissible tractive force, which was 19.62, and then we will calculate our y value for our assumption. From here, y value comes as 1.3 meters. We found y value. After we find y value, since our ratio was b over y equal to 4, we can calculate y value, b value easily. So basically, we will multiply this y by 4, and b will correspond to 5.2 meters. After find b and y, to decide discharge from the Manning's roughness equation, we need this area, we need this R value, you can see. So let's start calculating cross-section area, then we will calculate this R. Since we know N and slope, then we can easily calculate the design discharge. So there are two ways actually to calculate the cross-section area. The first way, you can use the basic geometry to calculate the trapezoidal area. What is that? Bottom width plus the top width divided by 2, and you'll multiply it with the height of this, or you can say flow depth. So what is T? If you look at this geometry, T is basically B plus 1x from right side and 1x from the other side. So this top portion for the area becomes B, and from T, B plus 2x. Now we need to decide what is x in terms of number. In question, we have given this z value, small z. What is this z value? This z value x is equal to this horizontal distance divided by the vertical distance. So basically x divided by y. We know y, we just calculated. It was 1.3, so 1.5 z is equal to, so this is z value, 1.5 is equal to x divided by 1.3, and from here x is equal to 1.95 meters, and I put everything into this cross-sectional equation. B was 5.2 plus b plus 2 times x divided by 2 and multiplied by y. So at the end, we find the area as 9.3 meters square. The second way to calculate, there is a direct equation given for trapezoidal areas in the page 46. Let me show it to you. Here, this is the equation. So it is area is equal to b plus z times y, close the parentheses, times y. You can also use this equation if your section is trapezoidal. They give the same result. And then we said we need this R value. We calculated the cross-section area. Now we need this R value. What is R value? It is A over P. We know A, then we need P value. What is P? P is basically the weighted perimeter. So what is weighted perimeter? It is the surfaces that water touches. So we need basically this surface, and this surface. We know B, so we need this and this. So how do we calculate this length? It is basically inside of a square root x square plus y square. It's from geometry, basic geometry. I wrote it here. We know x, we know y, we know b. B is 5.2, x is 1.95, and y is 1.3. And from this equation, P is 9.9. Or again, there is a equation given for the trapezoidal sections. If you know this small z, you can use this direct equation as well to calculate the valued parameter. Once we find cross-section area and P, we can calculate the R value. As I said, it is A divided by P. So 9.3 divided by 9.9, it is 0.94 meters. Since we found all the unknowns, now we can calculate the discharge value easily. 1 over n times A times R times 0. Of course, don't forget the powers. So basically, discharge is equal to 1 point from n is 0.02, A was 9.3. We find R as 0.94, and slope was 0.0016. From here, the discharge is 17.91 meter cube per second, which is very, very close to 18 meter cube per second. So it is acceptable, but we need to do some checks now. We found discharge is okay, but we need to do some other checks as well. What are those? First of all, we need to check for fluid number, and then we need to check for velocity. For fluid number, if you look at the page 49 this time, it says if R flow is subcritical, R fluid number should be less than 0.86. If it is supercritical, it should be more than 1.13. So let's calculate our fluid number. The equation for fluid number is velocity divided by inside of a square root g times d. What is d? It is a over t. These you can find this from your equations, open channel equations. And what is velocity? Discharge divided by the cross-section area, of course. And since we know all the numbers here, we know discharge was 18, cross-section area was, it should be 9.3. Gravitational acceleration is 9.81, cross-section area, again, it should be 9.3. I don't know why I wrote 1.31 here and 9.32 here. It should be 9.3 here and here as well. And what is T? We calculated here. It is B times 2 times X, B plus 2X's. So basically B plus, this is how you calculate 2 times X. So from here, fluid number is 1.931 divided by 3.17, and this corresponds to 0.61. So since it is less than 1, we have a subcritical flow. Since it is subcritical, it should be less than 0.86, which is less than 0.86. Therefore, for the fluid number check, we are okay. And now we need to check for velocity. If we go to the page 44, you can see minimum velocity should be 0.75 meter per second. Our velocity was, from here, we calculated, it was 1.931 meter per second. So it is more than 0.75. So velocity check is also okay. Therefore, our assumption was good. And we can just write our dimensions. And lastly, don't forget at this freeboard distance, which was the top of the water flow and top of this channel. This distance is freeboard from here to here. So in DSI standards, it is 0.73 meters. In USP-Air standards, it is 0.88 meters. I took this 0.73 meters, and if you add this 0.73 to this 1.3, at the end, you will get 2.3 meters, and this will be our dimensions. This is the end of question 2. Now I'll give a break and then continue with the third question.